In the previous topic, we discussed about the short circuited lambda by 2 transmission line resonator, and we found the equivalent circuit parameters of that resonator. In this topic, we will discuss about open circuited lambda by 2 transmission line resonator, and we will find the equivalent circuit parameters of open circuited lambda by 2 transmission line. As we discussed in the previous topic, lambda by 2 open circuited transmission line behaves like a parallel RLC circuit as shown in this figure. So this equivalent circuit parameters L, C and R, we can obtain those values in terms of transmission line parameters, that is Z0, alpha and beta of this transmission line, and the length L is equal to lambda by 2, and it is open circuited at the one end. To obtain the circuit parameters LCR in terms of Z0, alpha and beta and length of the line, we will find the input impedance of this parallel circuit and also input impedance of this open circuited lambda by 2 line at near the resonant frequency. So here for the lambda by 2 open circuited transmission line resonator, the input impedance, the resonant frequency is F0, and this is a magnitude plot of input impedance of the lambda by 2 open circuited line. As we can see from this figure, input impedance decreases above the resonant frequency, and also it decreases below the resonant frequency, and it is very high at the resonant frequency F0 as shown here. This is the resonant frequency. It is its length is equal to lambda by 2 at F0, and either side of the resonant frequency impedance reduces. It is very high at the resonant frequency. Similarly, for this parallel RLC circuit, input impedance is shown in this figure. Here also the input impedance is very high at a resonant frequency F0, and it reduces on either side of the resonant frequency as shown in this figure. So here, to obtain the parameters LCR in terms of these parameters, we have to find out the input impedance ZIN of both the resonators are near the resonant frequency F0. Near the resonant frequency means somewhere here. We have to find out the input impedance of both the circuits. Here, to find the input impedance of this LCR circuit, as we discussed in the previous circuit, it is LCR, the input impedance, because it is a parallel resonator circuit, it is easy to write the impedance admittance. So input admittance is given by 1 by R plus this admittance of this inductor, that is 1 by j omega L, and admittance of this, that is j omega C. So addition of admittance of each component gives the input admittance Yin. To obtain the input impedance, we have to take a 1 over of Yn, that is 1 over of Yn, it is equal to Zin. Zin is equal to, it is the inverse of this 1 by Yin gives the Zin. So this is the Zin input impedance. Now near the resonant frequency, we have to find out the Zin. Near the resonant frequency means that is at omega is equal to omega naught plus delta omega. So we have to substitute this value in this equation. By substituting this in the equation, we will be having this. Wherever omega is there, replace that by omega naught plus delta omega. And rearranging this, we will be getting this equation. This is the equation. Rearranging this, we will be getting this. And further, this 1 plus delta omega by omega naught to the power minus 1 can be written as 1 minus delta omega by omega naught. So after writing that, we will be left with this equation. So now here, dividing this by j omega naught L, we will be getting this equation. This is 1 by j omega naught L, 1 by j omega naught L, and this is minus delta omega naught, delta omega divided by omega naught j omega naught L, this one. So here this and this will be returned as it is. And now take 1 by R outside the all these terms. we will be left with this equation. Here, further writing this equation, rearranging the equation, we will be getting this equation. And again, as this writing this as r by j omega not L, and this is j omega not CR delta omega by omega naught. So in these two terms, R by omega naught L, it is equal to Q, unloaded quality factor Q naught. Similarly, omega naught CR, this is the unloaded quality factor of parallel resonant circuit, as we discussed in the previous topics. So we can replace this R by omega naught L by a Q naught. Similarly, this we can replace by a Q naught. So this again further it is equal to 1 plus J2 Q naught delta omega by omega naught. So we can rearrange this here like this. This is equation 1. So the input impedance of parallel resonator circuit near the resonant frequency somewhere here is given by equation 1. Similarly, we can obtain input impedance of this open circuited lambda by 2 line near the resonant frequency somewhere here, that is ZIN. So to obtain that, general expression for input impedance of open circuited transmission line we have to obtain. So here the open circuited transmission, in general the input impedance is given by this equation for a transmission line. Now if you write that ZL is equal to infinity for open circuited transmission line, using that you will be getting this Z0 cot hyperbolic gamma L. Again, assuming alpha is not equal to 0, we can replace this gamma by alpha plus j beta. So this is alpha plus j beta, Z0 cot alpha plus j beta. Now expanding this, you will be left with this equation. Now here we have to substitute you have to find a ZIN near the resonant frequency, that is omega equal to omega naught plus delta omega. So in this equation we should substitute omega is equal to this. So here to substitute that, beta should be written in terms of omega. So to do that, I take beta L, that is beta L is equal to, beta L is 2 pi by lambda, and L is equal to lambda naught by 2 at a resonant frequency. So it is lambda naught by L is equal to lambda naught by 2. Now writing this, we will be getting, multiply and divide this by pi, we will be having this pi omega divided by omega naught. So beta L is equal to this. Now substitute omega equal to omega naught plus delta omega and rearrange, we will be getting this equation. Now this tan beta L, by substituting beta L value, we will be left with this. It is approximately equal to pi delta omega by omega naught. So now this tan hyperbolic alpha L is, assuming alpha L is small, we can write this tan hyperbolic alpha L equal to approximately equal to alpha L. So using this tan hyperbolic alpha L approximately equal to alpha L, and tan beta L is equal to pi delta omega naught, and assuming this alpha pi delta omega by 2 omega naught is very much lesser than 1, equation 2 can be rewritten, this equation 2, using all these values in this equation 2, we can get this equation ZIN. Here assuming again this is Z0, and this we will be left with this alpha L pi delta omega by 2 omega naught by assuming, but this is very much small compared to this one. So this numerator is equal to 1. It is equal to 1. In the denominator we will be getting alpha L, and here it is j pi delta omega by omega naught. So this is the final expression for input impedance of this lambda by 2 transmission line, lambda by 2 open circuited resonator. The input impedance is given by this equation. Similarly, the input impedance of this Zn of parallel resonator RLC circuit is given by equation 1, and Zn of this lambda by 2 line near the resonant frequency is given by equation 3. Now, because both the behavior is the same, input impedance variations is same, we can compare the equation 1 with the equation 3. So by comparing equation 1 with the equation 3, we can get the parameters of this LCR in terms of Z0 alpha and beta. So by comparing equation 1 and 3, so this is the equation 1, this is the equation 3. Comparing these two equations, we will be getting R is equal to Z0 by alpha L, and C is equal to this pi by 2 omega naught Z0, and L is equal to omega naught square by omega 1 by omega naught square C. This is a well inductor value, and unloaded quality factor is given by this equation, that is pi by 2 alpha into L, or beta by 2 alpha. So those are the RLC values of equivalent circuit of lambda by 2 open circuited transmission line. So this lambda by 2 open circuited transmission line is equivalent to a parallel LCR circuit, and these LCR values these are the LCR values obtained as explained in the explained. So here the distribution of voltage over this line at a resonant frequency is given by this wave. So it is an open circuited transmission line at resonant frequency. Fundamental mode n is equal to 1. Fundamental mode of operation, that is at F0. The distribution of voltage is shown here. So it is maximum at the open end and at the input side, and its maximum decreases as explained, as shown in this figure. So similarly for maximum, and it is 0 here, so it is a maximum here and maximum here, and it varies like this over the length of the line. Over a lambda by 2 line, the voltage variation is like this for n is equal to 1, that is at F0, is operating at a F0 frequency. This is the variation. Similarly, this is for n is equal to 2. It also operates when at n is equal to 2 also. So this is the voltage variation over the transmission line with n is equal to 2. The resonant frequency can be calculated using this equation, that is F0 is equal to Cn divided by 2 into lambda. So using this equation, we can find the resonant frequency. For n is equal to 1, this is the distribution of the voltage. For n is equal to, this is the distribution of the voltage over the length of the line, lambda by 2. So this is we can obtain obtain the equivalent circuit parameters of this lambda by 2 line as by comparing the equivalent parameters of this input impedance of parallel line and the input impedance of the lambda by 2 open circuited line. We can get a parameters of equivalent circuit.